observing an object without coming into direct contact with it. So that being said, we can think about remote sensing not just at the satellite scale, right? It can be done at the airborne scale, tower scale, and scales all the way down to the leaf. So when we're talking about most all remote sensing approaches, we're talking about basically counting photons. So these photons travel from the sun and they reach the canopy, and then they're going to reflect back to whatever our sensor is, and we're basically counting photons in radiance units. And that's the basic principle. So when we think about remote sensing, we think about a few different types of resolution. And I think Zoe and Josh might talk a little bit more about this, but embedded in all remote sensing data, there's spatial information, spectral information, temporal information, and then if your data set can capture 3D data, we can get elevational data. So today I'm mostly just going to focus on spectral information and what we can and can't learn from the electromagnetic spectrum. Spatial resolution, this goes really without saying. This is just a image of a city as we increase pixel size, and there's obviously information lost, and then information gets sort of aggregated at these larger pixel scales. Temporal resolution, I think also maybe goes without saying. That's basically, we have time on the y-axis, we have some measurement on the x-axis. Let's say this is just biomass of some crop throughout a season. Might look like this. Our temporal resolution is how frequently either a drone flies over or a satellite flies over, or if we have, say, a tower-based remote sensing, we would get continuous data throughout that season. Okay, so let's get into spectral resolution. This will be sort of focus for the next 10 minutes. So the electromagnetic spectrum, I'm not going to explain what a wavelength is and amplitude. You can figure that out on your own. But when we're talking about remote sensing of stuff on Earth, we're mostly focused from the visible to sort of the infrared and shortwave infrared part of the spectrum. And that's what I'm going to be focused on today. Of course, the electromagnetic spectrum encompasses wavelengths across basically everything that's physically observable, but we're mostly just focused on this section here. Okay, so I'm going to talk about plant color for a second and why plants are green. So when photons come in from the sun, they have a spectrum, and that spectrum is pretty consistent. And it looks something like this, where it's peaking in the visible part of the spectrum, and then sort of slowly decreases as we go out into the near infrared and the shortwave infrared. And that incoming light we call irradiance. The reflected light we call radiance. And so this spectrum can give us an idea that by far the most energy coming from the sun is in the visible part of the spectrum, most likely why we've evolved to be able to see in the what we call the visible spectrum. And then also why plants are green, because that's where the most light is available. So of course, as this energy travels from the top of the atmosphere, some of it is absorbed, and the sort of, I don't know, more transparent region here is typically what's absorbed by the atmosphere. And then what reaches Earth is sort of this spectrum down here. And some of these dips are due to atmospheric absorption features. So why are plants green? Well, that's because they mostly absorb light in the blue and the red part of the spectrum. They also absorb light in the green part of the spectrum quite highly, but they reflect just a little bit more. And that's, of course, why plants are green. So why aren't plants black? Well, the first reason is it's just going to be too much energy and they'll probably overheat. The second is that we have a light saturation of photosynthesis under a certain amount of light. So the ability to absorb more light is not really going to do them any service. And then lastly, the penetration of light basically dictates why plants end up being green. Okay, so why are all these different wavelengths interesting? So again, if we have our sun here, and let's draw a cute little leaf down here. As these photons are traveling from the sun to the leaf, a certain fraction of them are reflected, which is what we see in this orange line here. And then a certain fraction of them are transmitted. And then a certain fraction of them, which Zoe will talk about more, are absorbed. And that's mostly in this visible region here. Okay, so the fundamentals of this cannot be explained in 15 minutes, but the way that plants reflect light in different parts of the spectrum all depends on how the leaves interact with light. And it can depend on biochemistry, it can depend on pigments, it can depend on leaf structure. And then at larger scales, it depends on canopy structure and what all is embedded within that pixel. So let's start with the visible part of the spectrum. So that's from 400 to 700 nanometers. And this is where plants absorb highly. So they absorb somewhere around 8% of the light in this region. And that's mostly due to absorption spectra of chlorophylls and carotenoids within that region. So if we exploit different sort of nuances within this part of the spectrum, and Zoe will talk about this a little more, it can tell us about how plant pigments might be regulating light. So this is just a model run from a model called Prospect at the leaf scale. And what you can see is that the reflectance, how the reflectance changes with changing foliar chlorophyll content. Remember, chlorophyll pigments really just absorb light in the visible part of the spectrum. And so as we increase our chlorophyll concentration, the amount of reflected light goes down, because that means there's more light absorbed by the plant itself. And so it's going to reflect less light. Again, this is our green part of the spectrum. This is the green hump. This is why plants are green. You can see changing chlorophyll content doesn't impact at all the near-infrared part of the spectrum. So when we jump to the near-infrared part of the spectrum, typically there's no light absorbed by plants. You can see that the transmittance line in blue and the reflectance line in gold sort of match each other. And typically plants reflect anywhere from like 30 to 65% of the light back to the sensor and back into the atmosphere, and that's typically due to leaf structure. So if we are to just change leaf structure with this sort of ambiguous parameter n that modelers like to use that has to do with leaf structure, we can see that most of those changes are happening in the near-infrared part of the spectrum, and some of them are happening in the visible. But really changes in leaf structure sort of manifest themselves predominantly in that near-infrared part of the spectrum. And then at larger scales, not just at the leaf scale, when we're making measurements of entire canopies, we get large changes in reflectance due to leaf area index. So as we increase our LAI from 0 to 6, for example, we can begin to see where these changes start to manifest themselves. So lastly, when we move out to the shortwave infrared part of the spectrum, there are some wavelengths here that people have attributed to plant phenolics and nitrogen and some other things, but it's prominently due to changes in the turgidity of leaves, so the leaf dryness and wetness. And that primarily has to do with these large absorption features in the spectrum, which absorb water strongly. And so if you have a leaf with a lot of water in it, it's going to absorb more light in this part of the spectrum and reflect less versus if you have a dry leaf. So if we just look at two spectrums of a wet leaf on the left here and a dry leaf on the right, so this would apply to this and this would apply to this, we can begin to see there's not actually a lot of changes that we observe in the visible and near infrared, but we see most of these changes in the shortwave infrared, and this can tell us a little bit about leaf water content. So all of this to say, what we can ultimately do with all this information is we can use what are called spectral signatures, where different components of the land surface all have different spectral signatures, and we can begin to differentiate between things like cloud, water, different states of vegetation, and snow in this context here. So you can see water is highly absorptive across the entire spectrum. And snow is highly reflective because it's white in the visible and near infrared. We can also use spectral signatures to differentiate species. And in this example, there's just 4 spectrum that are of 4 different species. One important caveat here is that the spectrum will change a lot just based on the status of the plant itself. So attributing it to a specific species can often be difficult. But we're beginning to see a lot more work being done to look at plant biodiversity based on spectral signatures. We can also do things with the reflectance spectra where we can begin to look at where spectrum varies, where spectra varies by different drivers. So I won't get into this in detail, but we can begin to look at where spectrally things might vary from, on this side, 400 to 2,500 nanometers, and on this side, 400 to 900, due to either, say, drought, or in this case, genotype, or in this case, over the course of an entire season. And then what we can often do empirically as well, which a lot of people have started to do with hyperspectral data, is begin to relate different spectral regions and features to different parameters that we measure at the leaf scale, whether that's pigments, stomatal conductance, leaf water potential, maximum photosynthesis. And this is where a lot of these sort of partially squares regression models come in, and people have empirically related plant biochemical or physiological parameters to reflectance spectra. So the last thing I'll introduce, and Zoe will get into vegetation indices in more detail, is just NDVI, which of course is kind of the original vegetation index and has been around since the 70s. And the reason this is effective is because it looks at differences in the near-infrared part of the spectrum and the red part of the spectrum, and basically looking at the differences in reflected light in the near-infrared and absorbed light in the red, we can learn a lot about plant greenness. One caveat to this is that often NDVI saturates at moderate to high biomasses. And that's because the amount of infrared radiance that's reflected begins to sort of asymptote under high biomass. And in the red part of the spectrum, we actually begin to see an asymptote under sort of moderate to high chlorophyll concentrations as well, as increases in biomass occur. So all that to say is that NDVI is more just a measure of greenness than anything else. I think oftentimes people attribute it to being healthy or unhealthy. Unhealthy is not necessarily true. It's just basically the amount of greenness or the sort of state throughout the season of that tree. So the last thing that I won't get into in detail, but I would recommend this book chapter, which came out a few years ago in the Remote Sensing of Biodiversity book that was edited by Janine Cavender-Barris. And this particular chapter talks a lot about challenges associated scaling from the leaf to the canopy. And again, this all has to do with a lot of different angular issues and different things that we can't get into in this talk, but have to do with how these photons basically interact with the canopy and ultimately send light back to our sensor. And that is all I have to say. And I will transition over to Zoe.
Okay. Hi, everyone. Let me. Okay. I think should be good with seeing that. Okay, great. Well, hi everyone, I'm Zoe. So I'm going to be talking about, I guess, specifically remote sensing of photosynthesis and the linkages between structure and function and how that can tell us about what plants are doing. So as probably most of you know, being in the flux community, we can observe plant carbon uptake or gross primary production, GPP, locally using flux tower observations. But remote sensing here is really a valuable tool to scale these observations from the individual site level to ecosystems more broadly. You can see there's a lot of ecosystems that don't have any measurements, many that are, maybe oversampled. And in the cases where we can't have flux towers in every single ecosystem across the globe, we need some way to kind of understand what's going on in areas that don't necessarily have these observations. Okay, so remote sensing metrics are typically based on the light use efficiency model of photosynthesis. And I'll relate that to GPP here. So plants absorb photosynthetically active radiation from the sun. A portion of that is absorbed by chlorophyll in a plant's leaves, or in this kind of schematic, needles. So that's the absorbed par, APAR, which is just the fraction of incoming light times the total light. And then from there, the light can go down one of 3 potential energy pathways. So the first we're all kind of most familiar with, which is photosynthesis. The second, plants will often absorb more light than they're feasibly able to use to drive photosynthesis. And so they have a well-regulated pathway that can safely dissipate this absorbed energy as heat. And based on the dynamics between the partitioning of light between photosynthesis and heat dissipation, we can say that over the entire canopy, GPP, gross primary production, as would be measured by a flux tower, is equal to the fraction of incoming light that a plant absorbs, which is just the fraction times the total, times the light use efficiency of photosynthesis. So how much of that light is being used to drive photosynthesis. The final pathway, so then remote sensing metrics will typically be either sensitive to the physical factors, so the amount of light that's absorbed by chlorophyll, so kind of this FPAR term, or physiological factors, evaluating how much light is being sent down this heat dissipation pathway and therefore photosynthesis. The final pathway for this light is that it can be re-emitted as solar-induced fluorescence, which in fact tells you both about the physical and the physiological factors. But I'll explain a little bit more about that in a bit. So as Troy talked about, the normalized difference vegetation index, NDVI, is generally sensitive to canopy chlorophyll and thus FPAR. And so if it's giving us a measure of how much chlorophyll is available in a vegetated area to absorb light, it's giving us information about this FPAR term and integrated over seasonal timescales, over broad spatial scales. If we know how much chlorophyll there is, it can generally be a good measure of kind of an area's capacity to perform photosynthesis. And so here's just the NDVI calculation, and this is great because we can measure it all over the place, and NDVI has a long history of success in approximating GPP and plant productivity. Since then, there have been, so NDVI tracks GPP really well in systems where canopy structure or chlorophyll content are strongly correlated with productivity. So this is particularly true in deciduous forests, or here is data from a cropping system, a wheat field, where you can see GPP and NDVI over the course of the season just correspond really well, and have a really good correlation here. And that's because NDVI is largely sensitive to this chlorophyll content, with these other terms staying more or less constant over this temporal scale. Expansions of NDVI, such as EVI or NIRV, can help account for additional nuances in the NDVI signal. So soil background can impact the signal, or atmospheric effects, as well as the saturation that Troy talked about. And so here you can just see NIRV and monthly GPP, which again, NIRV is sort of an expansion on NDVI that also measures greenness, with good correlation between GPP and NIRV. And again, this is because these are corn and soy systems where canopy structure, the amount of chlorophyll, corresponds really well to how much carbon plants are taking up. And I would also highly recommend this paper by Yelu Zhang that has a really nice table that describes a lot of these different vegetation indices and kind of the primary application advantages, disadvantages, why one might be better for another kind of depending on the situation. So unfortunately, greenness-based vegetation indices, so NDVI, NRV, etc., do a really poor job at tracking GPP in evergreen ecosystems. And that is because canopy structure and carbon uptake are not closely correlated. So here you can see January versus July of an evergreen forest in Colorado. Canopy structure is completely the same, but over the course of the season, GPP changes dramatically, whereas NDVI is completely flat. And so we need other metrics that are sensitive to these physiological factors, because since this is not changing in this type of ecosystem, this light use efficiency of photosynthesis must be changing a lot. So we can revisit this kind of 3 pathways structure, and there in this heat dissipation pathway, there are 3 compounds that can essentially regulate how much, oh, sorry, there's like trucks going by outside, how much light goes down this heat dissipation pathway. And depending on the amount of these chemicals, it will actually change the reflectance or spectral signature of the plant. So this is kind of the same plant in winter versus summer. And you can see that here there's a big change in the reflectance signature. This figure has been shown kind of a bunch of times, so I definitely recommend some of these papers for kind of a further explanation of where to look in the spectra. But one good example of this is the chlorophyll carotenoid index, which uses MODIS spectra or reflectance bands. And as you can see, these are a spruce and a pine forest. CCI does a really good job tracking GPP over the course of the season, especially in these periods of dormancy due to winter, and that can be largely attributed to the fact that the light use efficiency of photosynthesis is really dynamic in these systems over a course of a season, whereas the FPAR term is fairly constant over a course of the season. So models to predict GPP based on remote sensing vegetation indices that include information on both structure and function ultimately do a better job. Here's a figure from a recent paper by Chris Wong. Sorry, there's a lot going on in this figure, but essentially this was building a bunch of different models to try and predict GPP, and then the change in GPP from the prediction versus the actual. And what we can see is that the models that have both something like NDVI, so that tells us about structure, as well as the light use efficiency of photosynthesis, the function, do a better job at predicting GPP than those that do not. In the same vein, solar-induced fluorescence is sensitive to both structure and function, so it generally is a really good proxy for GPP compared to CCI or NDVI, although here you can see CCI does a really good job, but compared with SIF, which generally does a much better job over the full course of a season. I'm not going to go into the details of why it's sensitive to both structure and function, but if you have questions about that, I'm happy to chat later. Okay, so studies at the leaf and tower level have also highlighted nuance to the relationship between SIF and GPP. So at low spatial and temporal resolutions from satellite, we generally see a linear relationship between SIF and GPP. But higher spatial and temporal resolution, there's been a lot of studies coming out as of recent that show places where SIF and GPP diverge. There's also this curved structure between SIF and GPP. So it's a nuanced relationship. It's not kind of maybe as one-to-one as we might like it to be, but generally the utility of SIF and other remote sensing metrics depends on your spatiotemporal resolution. And I'm going to draw your attention to panel D here, where this shows the photochemical yield and the fluorescence yield. So essentially how much light is going down the pathways of photosynthesis or fluorescence. And the majority of remote sensing observations fall in this part of the curve here, where plants are not under low light or extreme high light, non-stressed. And so we generally have a pretty linear relationship between the two. I would also recommend this paper if you're interested in learning more about the nuances between SIF and GPP and why there might be divergence or convergence between the two. Okay, and then in the similar vein as vegetation indices, models to predict GPP based on SIF as well as vegetation indices do generally a better job than SIF alone. So here's a figure from one of my recent papers that uses a random forest model combining SIF as well as vegetation indices that tell us again about both the structure and the function of the plants. And we get a really good agreement between the GPP that's predicted from this model and measured GPP across multiple different sites. Okay, so some conclusions before I pass it over to Josh. So remote sensing can tell us valuable information about ecosystems when flux tower data is not available, or we want information that we can't measure with fluxes. So pigment data, understanding kind of the photosynthetic capacity of ecosystems. There's also no one remote sensing metric to rule them all. It all depends on what exactly you're interested in. If it's the structure, the physiology of the plants, maybe it's both. Ecosystem type. So again, for a cropping system, NDVI is probably something that works great because the structure and gross primary production are probably very closely correlated in that type of ecosystem, whereas in evergreen ecosystems, that might not be the case. And the temporal scale that you're looking at, so whether it's seasonal, diurnal, or if it's a kind of a short-term stress response, different remote sensing metrics will potentially tell you different things or be more or less applicable for that temporal scale. And with that, I will pass it over to Josh.
Great, thanks, Zoe. And if you in the audience feel like this is going really fast, it is. It's even fast for me, and I know all this stuff. So it's all really good stuff that Zoe and Troy have gone through. Kung is recording it. So it will be presumably released maybe on YouTube where you can watch it in half speed and you know, with lots of pauses to catch up on all the dense slides that we've been showing. So to close out the two, and remember, this is also like the first of like a whole bunch of stuff coming from Ameriflux on the year of remote sensing. So Zoe, Troy, and I are giving kind of a brief overview, quick introduction, lots of hooks, as Troy said, not really going into anything at depth, but just to give you a feel for the broader landscape of remote sensing and as it applies to a lot of the interests of the kind of the Flux community. And there'll be other tutorials. There'll also be kind of more in-depth data workshops where you know you can work with the data. Definitely feel free to email Zoe, Troy, or myself questions, no matter how small or big. We're also on Twitter, and that's good for like you know common questions that discussions that might be of interest to everybody. Or to more than one person. So, can you see this okay? Zoe, give me a thumbs up because I can see. Okay, cool. So I'm just going to give you kind of a quick overview of lots of different types of remote sensing products that are relevant to terrestrial ecosystems. Troy and Zoe definitely went very in depth into photosynthesis and greenness and fluorescence and things like that. This is going to cover an even broader scope. Again, not going into much depth about any of them except a little bit on ET, as it's a little bit more relevant to the Flux community and also one of my big specialties. So to kind of motivate remote sensing, we can ask how well are ecosystems sampled. So if we look at land, you know, there's a little bit more land in the higher, in the northern latitudes. This is GPP, right? Our breathing of the biosphere. Most of it's in the tropics. And then where's our total carbon? There's a lot in those tropical forests, but there's also a lot in Arctic and boreal forests and ecosystems and soils. And so if we think of these two poles of the carbon cycle, how well are they sampled? And if we put our flux measurements, our flux dent measurements on this chart, they, you know, end up being in the US and in Europe and in kind of the mid-latitudes, the northern mid-latitudes, which Zoe showed in map form just before. And so we can see that our carbon cycle is woefully undersampled when it comes to our flux measurements, as Zoe had mentioned. So that's where remote sensing can come into play to help fill these gaps and scale outwards. And there's a lot of measurements. This is just the NASA Earth fleet, and like this is from August, and like it changes almost like, you know, every month as a new mission flies or a new mission comes down too. So an old mission comes down. So it's dynamic, but there's lots of Earth missions, you know, more missions kind of looking back at Earth and looking away, which most people don't even realize about NASA and the European Space Agency and JAXA and lots of different commercial companies as well. And on the International Space Station alone, there's a whole bunch of missions looking back at Earth, whether it's EcoStress or OCO3, JEDI, and so on. So we have an absolute wealth. If we kind of link back to what Troy showed earlier in terms of the electromagnetic spectrum, you can take any bit of that electromagnetic spectrum and kind of make a product that's relevant to ecosystems. And that's why we have lots of different missions, lots of different products. Why isn't it all on one kind of enormous hyperspectral mission? Well, because it's engineeringly difficult to do, and you don't want to mess that up. So that's why we end up having lots of missions. Zoe had mentioned, you know, there's many lenses to looking at ecosystems, whether it's through structure, composition, or function. And when we put these lenses together, you know, the kind of the true picture of ecosystems emerges, spotlit by different forcing factors. So if we look at carbon to start with, Zoe talked a lot about green, or Troy and Zoe talked a lot about greenness. And so these greenness products, whether it's NDVI or these other greenness products built from essentially the near infrared part of the electromagnetic spectrum and the red or maybe splashes of blue and so on. You know, sometimes we think greenness can tell us everything. Greenness can tell us photosynthesis. Greenness can tell us evapotranspiration. Greenness can tell us, you know, and it kind of can, but it, you know, it's not really there. But there's a lot of derived products that come out of greenness, these greenness products. And some of them are more real than others. And so that's something to question. I think, yeah, Troy had mentioned you can start to get a land cover, which is very important. And I don't think Troy or Zoe talked about active remote sensing that much, but using LiDAR or even radar, we can start to get at canopy height. And in this paper here, with Mark Samard as the lead, we actually compared it to canopy height measurements from as many FluxNet sites as we could for the validation. And from canopy height, you can start to get a biomass. Sasan Sachi and lots of others have really created amazing global products of biomass from remote sensing. On the International Space Station is the JEDI instrument, and it's a LiDAR. And here are kind of some features of it, basically getting us 25-meter resolution. Not really kind of wall-to-wall mapping, but they create a wall-to-wall map from those point measurements. Zoe talked a lot about fluorescence, so I don't need to talk too much about that, but it's definitely good insight into photosynthetic activity where greenness will fail you, as she pointed out from Troy's paper. And there's lots of different measurement instruments, whether from the US, there's multiple ones, from JAXA, from ESA. So you're going to see lots of different fluorescence products or missions that are giving different data products. And they all have their differences and nuances. And so it's sometimes kind of confusing to figure out which one should you use and which one, you know, is better than the other. But, you know, lots of people work on that. For hyperspectral instruments, there hadn't been many instruments for a long time since something called Hyperion, but now there's a bit of a hyperspectral renaissance. DSIS went on the space station actually in the same rocket as EcoStress. We were both at the launch pad in Florida hanging out, and we're like, who are you? And we're like, well, that's useful. And so they went up, and then Hisui is another one that does hyperspectral, and then recently Emit just went up on the space station to do hyperspectral remote sensing. So you can do lots of interesting plant type products from spectroscopy or hyperspectral remote sensing. As Troy had mentioned, they kind of related to different features of plant structure or composition. You can even start to break it down to species level, canopy nutrients as well. And some of my work recently has been looking at, with Dan Souza, a former postdoc, looking at getting mycorrhizal associations with hyperspectral. We can start to put some of these together to get at nutrient limitations. So if you got a lot of water and energy, you're going to have a lot of evapotranspiration. You're also going to have a lot of greenness. But we asked some parts of the world you don't have a lot of greenness, and you still have a lot of water and energy. Why? And you could chop down the greenness through deforestation, or you might not have enough nutrients. All right, so getting more into some of these water products. If we look at the kind of water cycle, we're especially interested in water resources as well. So we've got rain and snow, evapotranspiration, we've got our surface soil moisture and our deep groundwater and our runoff. And we can actually measure every component of the water cycle and more remotely. So for the longest time for rainfall, we just mostly had it in kind of geostationary or tropical. There's a tropical rainfall measuring mission. Now there's the global precipitation measurement constellation, which is a multi-agency constellation of satellites to do rainfall. For snow, we can see the snow if it's there or not, but it's still a little bit hard to get at snow water equivalent and snow depth. There's airborne capabilities like the Airborne Snow Observatory, and that'll Tom Painter runs that, and there's other similar capabilities where you'd fly LiDAR over a mountain before it snows and get the surface, and then after it snows and the surface gets a little higher because of the snowpack. And so that'll get you the snow depth and albedo, which will tell you the melt rates. Evapotranspiration is something that I've worked on for a while, and started working on it from a satellite called AVXR, moving into MODIS and Landsat, and then into EcoStress and now HydroSat. SMAP is the Soil Moisture Active Passive mission. It was an active radar and a passive radiometer. The active radar basically sent this radar pulse down from the satellite into the mud or into the dirt and bounced back, and it told you how wet the soil was. The radar doesn't work anymore, but the radiometer still works, and it takes the solar reflectance and gives you the soil moisture, which is quite useful for ecosystem dynamics. It can also be useful for getting at wetlands and other types of missions, including radar and the upcoming NISAR mission will get us wetland and inundation, as well as freeze-thaw dynamics. And these are products out of SMAP and other missions as well. We can actually get at the deep groundwater using gravity measurements, using the twin satellites of GRACE, which have now been succeeded by the GRACE follow-on mission. And they basically kind of get pooled to the earth when there's more mass, when you have a lot of groundwater. And if you kind of suck out all that groundwater, the next time they fly over, they'll get pulled to the earth a little bit less because mass pulls, gravity or creates gravity. So that will get very high precision and that kind of deep mass change often associated with groundwater change. And then the last water cycle component, which would be river discharge or river runoff. again, using active remote sensing radar, like that airborne snow observatory, you can shoot that beam down on rivers and it'll tell you how high the river is, which, you know, is correlated with how fast it's flowing. And you can also get like lake heights and reservoir heights and things like that. So the SWAT mission actually just launched a couple months ago, I think. There's EcoStress, which I was the science lead for at JPL, and that focused on evapotranspiration using thermal measurements. So I'll give a little bit more deep dive into EcoStress. It has heritage from a number of missions on using surface temperature, ASTER, MODIS, Landsat, and so on. And so we get surface temperature and emissivity. And so that'll allow you to pick up interesting temperature dynamics like urban heat and fire. That was from NOAA and then to MODIS, and now this is created from EcoStress. This is fires in California from 2020. And this is what the swath kind of looks like on the right, where it flies over kind of the central US into Texas. And then you can see the detail of the evapotranspiration that we derive from the surface temperature measurements across all the pivot irrigation fields. And this is in Garden City, Kansas, seeing kind of the heterogeneity and the detail of the managed landscape. Here's an image in California, in Central California, moving from the Central Valley on the left with all the fields up into the drier foothills, kind of where like Tonzi Ranch is and Vira, which some of you might know from the Flux community, Dennis Baldacci sites, and then up into the Sierra Nevadas on the right, where it's a little bit colder and wetter. Here is that swath flying over the southern Amazon. You can see in the bottom left that inset of the swath and the zoom, and you can see kind of that arc of deforestation going on, but also within the Amazon rainforest, the intact forest, you can see the mosaic of evapotranspiration that's occurring. EcoStress gives us multiple overpasses at different times of day, and so here is an image over the Nile Delta, where EcoStress passed over at about 6 in the morning, where the kind of fields were just starting to wake up and evapotranspire. And then again, it passed over in the afternoon around 2. And you can see the fields are really cranking. The color bar scale is, you know, even higher. Although some of the fields are starting to dry down a little bit. So that's something that's interesting from a diurnal perspective. And given that good spatial resolution, you can start to see what's going on. So when EcoStress first launched, we did a lot of validation against eddy covariance sites around the world, as well as surface temperature measurement validation sites. And so this was kind of the validation for EcoStress that we were able to get like kind of more real time right when the mission launched to just do quick kind of sanity checks on the data. And there's a lot of processing issues to deal with in terms of clouds and aerosols and things like that. There's also water use efficiency product created out of EcoStress, and you can start to see these gradients of water use efficiency. There's also a drought product called the Evaporative Stress Index product, and that'll tell you kind of when plants are facing water stress or heat stress. And that'll tell you, stress before NDVI will tell you their stress. And also give you kind of indications into wildfire, potentially where wildfire will spread into high stress parts of the forest. You can see on the left, if you didn't know the stress, you would just see fires on kind of a green mosaic of Amazon forest. But on the right, when you kind of give that X-ray of stress from the thermal measurements, you can start to see that the fires are kind of spreading into the higher stress areas. So we're talking about the future of evapotranspiration. I'm now the science lead for Hydrosat, where we're launching a constellation of measurements, basically 16 plus satellites to give us really, really high resolution measurements of temperature and evapotranspiration every day. And so right now, if you were to kind of look at the weather report, you might get a high resolution measurement once every 16 days from Landsat. And in between, you'd get some kind of a coarse resolution from MODIS, but with Hydrosat, we're now filling that all in at higher resolution. And so again, now really trying to be able to see the detail throughout the landscape, both in visible near infrared and thermal infrared. And there's synergies with CubeSats from like Planet. Planet is giving us daily 3-meter visible near infrared. Former postdoc Bruno Aragon, now at Planet, is working on using Planet data to retrieve evapotranspiration at really high resolutions, which is really incredible. And so now, if you look out onto your, landscape or your agricultural landscape or your ecosystem, we can now have really detailed information as to what's going on. So that's kind of a snapshot of lots of different measurements and missions. I just want to give you a few kind of perspectives on what to do with all these measurements. So satellite missions are traditionally independent of one another. And one launches, the next one has a different team that launches with different science objectives, and they're typically disconnected from one another. And then by the time the next one comes along, the first one has ended its lifetime. So it's kind of really difficult to piece these together to produce like a coherent, cohesive picture of ecosystems. As one comes in, one comes out, the other one is the wrong resolution, and so on. That's changing a little bit, especially with NASA and a lot more interagency collaboration in the Earth System Observatory. But that's traditionally how it's been, and it's difficult to put them all together. It's basically just budgetary at that point. So there's a challenge there. And just putting in a few slides from a talk I gave at AGU, it's also on YouTube. Oftentimes for ecosystem scientists, we're interested in plant stress. Can we pick up the transpiration and the photosynthesis cessation? Can we pick up the leaf angle and the wilting? Can we pick up the damage and the loss, the dormancy and eventual mortality? And hopefully after seeing these talks from Troy and Zoe and the slides I presented so far, you can start to think that, here's that kind of inverted pyramid of plant stress responses. And now you can start to put on different remote sensing measurements onto each of these, whether it's from ET or fluorescence for the top bit, or structure for the middle, or hyperspectral and on down. But we do want, as we often say, Dennis Baldacci often says, we want fluxes everywhere all the time, and we also want plant stress responses everywhere all the time, and early, right? So we can do something about it. So for structure, we talked a lot about visible and near infrared and active remote sensing and LiDAR and radar. And so one thing we've only kind of touched on a little bit is the kind of what do you get in terms of characteristics. And usually there's a trade-off between high temporal resolution and high spatial resolution. You can see you kind of get one or the other, and you never really get both. And that's been a challenge. Planet has come along and launched their constellation to get visible near infrared every day at high spatial resolution. So that's good. But that's not the same with everything. And then where does it fall on the early warning indicator? Yeah, you get right around there. And LiDAR and SAR will tell us kind of that final death story, which will tell us, about stress throughout the rest of the forest early, but too late for the individual, trees and so on. For composition, there's spectroscopy that'll get leaf damage, stress, disease, pigments, and so on. Right now we're kind of in this, renaissance of spectroscopy where we've got lots of missions coming up. They're all about the same though, kind of this similar spatial resolution, similar temporal resolution. NMAP will be a little bit better out of Europe. and that tends to do a pretty good job. We've also got the radar and vegetation water content, and that's giving us even better early warning. And then for function, we have that thermal for ET and fluorescence to start to get productivity. And again, the thermal, like the visible near infrared, we had that trade-off between high spatial, high temporal. We're getting more thermal emissions with SBG and a few out of Europe with LSTM and Trishna. Hydrosat's coming along with the constellation like Planet on the thermal side. Fluorescence had traditionally been out of the atmospheric community, so much less interested in spatial resolution, although that's changing rapidly. And fluorescence does a great job getting early warning, and so does thermal. And so, yeah, so this is kind of where they all lie on the space-time graph. So synergies, when you start to put them together, and we had outlined this a little bit in a paper when it was in 2017 on just using the space station alone. But when you start to put together, evapotranspiration and photosynthesis, then you get water use efficiency. And so you often don't get both those products from the same mission. You have to combine them together. For EcoStress, we did, but we actually started off using MODIS for the GPP. Now we're using our own model called BESS out of Young Real Reuse Lab. But you can kind of see this smattering of different intersections. And that's what really terrestrial ecosystem science and terrestrial ecology is about the dynamics, whether it's structure, composition, or function, or across these types of measurements to get us more detailed understanding of how the complexity of ecosystems work across measurements. And one last bonus is soil moisture, a key driver of ecosystem dynamics. And that's kind of marched forward from Europe out of SMOS into SMAP, and then now into NISAR coming up. And that's really off the chart. It really gives us really good early warning. So kind of that wraps up my quick overview, kind of the one-stop shop of lots of different products, the Amazon.com for looking at the Amazon basin, so to speak. It's really about kind of understanding how these connect with our community, our analyses, and hopefully one thing that one big message that you got from my talk was that it's about working together, across missions, across agencies, across different types of expertise. When it comes to climate change, it's super dynamic, interdisciplinary. It's hard to do it all oneself. And so the more we can work together, the more we'll solve these big problems and grand challenges. And with that, I leave a few minutes to Kung or questions or anything that Zoe or Troy might want to add.
All right, Josh. Thank you so much, Josh, Troy, and Zoe, for the great overview of the current state of remote sensing and theories. And please keep thumbs up to them. So yeah, I think we have 4 minutes left. So if anyone has some questions to our instructors, maybe we could do some Q&A. You can leave your question in the chat, or you can just speak up if you like to.
I have a question. Thanks everyone. That was a good, quick, fast overview. I feel like, Josh, maybe you and I have kind of talked about this, but I've been thinking about this more and thinking of the synergies of the instruments. And Zoe, I know you kind of talked about this with the CCI, but I feel like I'm curious what folks think about using, especially Josh, you talking about this uptick in hyperspectral and utilizing the entire spectral fingerprint per se, and how what, I feel like all of you talked about NDVI and how this is that textbook one, but it doesn't always answer the question that we're after. And so I'm just curious what your opinions are on utilizing the hyperspectral data to its full advantage. And I mean, because there's a lot of information there, and kind of any advice you have on that.
Yeah, I mean, I'll quickly say that there is no good answer to that, Jen. It's like just an active field of discovery and remote, and investigation. NASA's like, really, and especially JPL is really pushing on that before launch of SBG. And I think Troy referred to kind of some work by Sean Serban and Phil Townsend, who've really been pushing the frontier on that as well. But yeah, it's a big frontier in terms of how to actually use, to kind of restate your question, Jen, how to use that, like all the different bumps and wiggles of the spectra to get at part of things that you want to know in terms of plants and plant dynamics, and how to make that universal and not just calibrated to a single site. So that's still like, pushing the frontier. Troy and Zoe, you want to add in?
I mean, I can say quickly, like one thing to consider when beginning to sort of interpret these hyperspectral data sets is what is actually sort of the mechanistic reason why wavelengths are changing in the way they are, and is what we're seeing truly biophysical or biochemical, or is it purely empirical? And I think in many cases, because plant traits vary so much across space and time, it makes it so a lot of these empirical approximations of something like Amax or stomatal conductance can work well because of the ways that plant biophysics and biochemistry sort of change. And I think one important thing as we get into this space to not sort of forget is the mechanistic underpinnings for why wavelengths are changing the way they are.
Right.
Cool. Thank you.
Yeah, I think there was someone else, Jason Horn.
Yeah. So going off mechanistic underpinnings and the relationship to certain spectra, what are your opinions on our abilities at this point to pick up on the xanthophyll cycle and using that? Things like PRI and CCI, are they at a point where we can use them to try and gauge light use efficiency well, or is there still more work to be done? And going off of that, is there one that is better than the other? I know you guys talked about CCI, or Zoe talked about CCI, but is PRI also a valid indice at this point in time, or is it kind of obsolete? I'm just kind of curious.
So I think kind of as one of my concluding points is that it depends on your spatial and temporal resolution. So PRI, I would say, is more applicable if you're looking to track shorter term heat dissipation, so within the course of a day. And so then your spatial scale would also be much smaller. PRI also tends to have more kind of artifacts with viewing directional effects and things like that. And then CCI was kind of designed to be sort of these bigger spatial scale using the MODIS bands for seasonal timescales. So it just kind of depends on what, I guess, more specifics of the question that you're asking is what metric makes more sense. Did that answer the question?
Yeah, no, that's awesome. This is a really great talk. So thank you guys for all this huge wealth of information.
I'll say quick, Jason, to your first point, the nice thing about PRI and CCI leveraging changes in that 532 nanometer band is that that's been shown to be directly related to xanthophyll pigment interconversion. So it's more mechanistic in that way because it is telling us about how these carotenoid pigments are shuffling around over the course of the day and over the course of the season.
Awesome. Very cool.
Okay, is there any other more questions from the audience? Okay, if not, then thank you everyone for joining us today. And yeah, today's session is recorded and will be uploaded to the AmeriFlux YouTube channel in the coming days.
Actually,
and as
I was just trying to answer Sandra Duran's question. Before you close the Zoom, otherwise I won't be able to chat the answer quickly enough. But it's actually a pretty relevant question. She asked kind of more generally when you're comparing, and this might be a good question for Zoe too, when you're comparing remote sensing to flux sites, the flux sites are giving you measurements every 30 minutes or every hour or 10 times a second, really. But the remote sensing is flying over, once a day, at 17,000 miles per hour or whatever it is. So it's instantaneous essentially, unless it's a geostationary satellite or it's a weird thing like ecostress. So how do you deal with that? How do you deal with that temporal diurnal resolution mismatch? There's different ways to kind of to take that instantaneous measurement and guess at what's happening throughout the day. But it's hard to do. You can take your in situ measurements and scale out from there, but it's ultimately a guess. And if you got clouds coming in the afternoon and you didn't account for that, then you're going to be wrong. People have fused geostationary satellite observations, which are like continuous over the same spot, but very coarse spatial resolution, with some of these other types of measurements. But it's definitely a challenge for sure. So remote sensing definitely kind of reigns supreme over spatial coverage, but is very wimpy when it comes to temporal coverage. I don't know, Zoe, do you have anything else you want to add to that?
Well, I think that this is one of the kind of exciting and like emerging opportunities for tower-based remote sensing too, is when we have sites with tower-based remote sensing, we can validate some of the assumptions that we make about how representative this kind of big snapshot measurement over a huge spatial scale is versus these tower-based remote sensing measurements, which are more or less the same spatial and temporal resolution as the flux tower observations. So I'm biased because this is also the kind of niche that I work in, but I think that that's kind of a great opportunity for tower-based remote sensing.
Okay, I think, yeah, we're over by a few minutes. We can give people back their days.
Okay, yeah, thank you so much for Q&A and everything. Thank you everyone for joining us. And so there will be another 2 more installments in February, and we will share more details soon. So until then, and take care, and we'll see you again soon, and have a nice day. Bye.
Yeah, thanks for coming, and feel free to reach out to us on email or Twitter if you have any more questions or discussion.
Thank you. Bye-bye.